Okay, so today we're going to look at substitution using Newton's universal gravitation law. If you remember from the last discussion we had, we said that this is the equation that Newton discovered where the force of gravity between two objects depends on the universal gravitation constant, which is big G, and the mass of each item, and then the distance between their centers squared. We looked at this. This is an inverse square law, so the further you get away from an item or two objects, the further they get away from each other, the force decreases exponentially based on that distance. So let's say, for example, that we want to figure out how the force is affected when we alter either the mass of the objects or if we alter the distance between them. We can do that by some substitution. So I'm going to show you that process today, and then that's what you're going to be using in your homework this evening, is that process. So let's say, for example, here we have some initial gravitational force which we're going to call F old. So it's our old force of gravity, and we're going to compare that to some new force of gravity based on some changes we make either in the mass or in the distance or both. So let's look at how this works. So let's say, for example, that it says we wish to double one of the masses. So our new force, what are we doing to one of the masses? We're going to make it, instead of m, it's going to be 2m. Now what we can do is we can bring that 2 out front of the entire thing. Correct? I mean, algebraically we understand that if the 2 is in the equation, we can bring it right out to the front of it. And what is this right here? What is gmm over d squared? That was the original force, or the old force. So we're going to substitute that in right here. That's F old, and what goes in front of F old? 2. So how does the new force compare to the old force if we double one of the masses? It's twice as much as the old force. Do we see how that is represented there? So if we double a mass, the new force is now 2 times the old force. Pretty straightforward? All right, let's look at the next one. This time we're going to keep the masses the same. We're going to double the distance. So again, remember the distance is squared, so if we double the distance, it's going to now be 2d squared. And what does 2d squared come out in the front as? Be careful here. Okay, first of all, it's in the denominator, and it's squared. So it should be 1 over 2 squared, or 1/4. Okay? So it's either 1 over 2 squared, I'm okay with you showing that, and then you could just say it's 1/4 the old. So if we double the distance that two objects are away from each other, the force between them is now decreased by 1/4. I'm sorry, it's now 1/4 as great as what it used to be. Does that kind of make sense how that works? Okay, this is the one that's a little bit tougher. Okay, so now we have two planets. We have Earth and we have this other planet. So Earth is going to be like our old force. Okay, where we have the force on Earth is going to be gm times the mass of Earth divided by the radius of the Earth squared. And again, if you remember last time, here's the Earth. If we're sitting on top of the Earth and we want to know the force on us, what's the distance between our center of mass and the Earth's center of mass? That would be the radius of the Earth. Okay, so that's how that comes into the equation there. And then one of the objects is whatever we're dealing with. So in this case it would be us, and the other mass would be the mass of the Earth. What do we know about our new planet? It's 500 times Earth mass. So in our equation, what are we going to put next to Earth, the mass of Earth? It's 500. So our planet is 500 the mass of the Earth. Everybody see that? So the mass of the planet we're substituting in 500 ME. Everybody see that? Now, what's it say? The force of gravity on the planet is only 3 times larger. So the force on the planet is going to be equal to what times the force on the Earth? Good. 3.0. And what's it asking? It wants you to determine how the radius of the planet compares to Earth's radius. So the planet radius is going to be x times Earth's radius. Do you see how that gets substituted in there? Yes? Okay. Now, what stays on this side? 3.0. And what can we bring out front in this equation now? We'll bring the 500 out in the numerator and x squared in the denominator. Good. And see, everything else stays the same. We have g m me divided by re squared. And what is g m me over re squared? F old, or F of the Earth. Okay, the force due to Earth. So, what stays on this side? 3.0 over here, 500 over x squared, force of the Earth. How do we solve for x? You could, but if you have FE on both sides, what can you do with it? They cancel, right? If you divide by FE, they cancel. So now we have 3.0 equals 500 over x squared. So what does x equal to? The square root of 500 divided by 3.0. See where I got that? I multiplied both by x squared, so I have 3.0 x squared equals 500, and then x squared equals 500 over 3.0. So x equals the square root of that. So then x then equals, or 13, because if you look at digits, it should actually be 13. So what is that saying to us? Look back at your original. The radius of the planet is how many times larger than the radius of the Earth? 13 times the radius of the Earth. Does that make sense? So radius of planet is equal to then 13 times the radius of the Earth. And we didn't use any other numbers. We didn't know what the force was. It didn't matter. It could be any object. Okay? So all we're doing is we're looking at how do we change, or if we change the force, if we change the mass, if we change the radius, how do those things affect the overall? That's what we're looking at today. So tonight you have 6 problems. Pretty straightforward. You have to show this method. So for example, number 1. A force exists between 2 masses. I want all of us to do number 1 together so you can see exactly what I want you to do for your homework. Okay, so I'm going to show number 1 up here. So the first thing we need to do is establish what F old is. F old is GMM over D squared. And once you do that one time for the entire assignment, that's fine. That's all you have to do. One time. F new. What are we doing in problem 1? Doubling what? Both masses. So now it's going to be G times, what's this new mass? 2m times 2m. We double both masses over D squared. What comes out front?
4.
So F new equals 4 times GMM over D squared. And then what is GMM over D squared? F old. This is what I'm looking for. To get full credit, those are the steps I want to see. Pretty straightforward? That's it.